Hey there everybody. In this video we're going to work some examples using what we've learned about Ohm's law and the energy dissipated by a resistor in a circuit. So we're just going to work through a couple of examples together to kind of give you a better idea of how we use what we've learned to solve some simple problems involving circuit. So the first example that we have a random battery connected to a 40 ohm resistor. So remember that this symbol is pronounced ohm. And the current through the resistor is measured to be 0.2 amperes, or here in America we might just say amps. And we're asked to do a couple things with this. We're asked first of all to draw a circuit diagram. So what I might do is draw a battery first. So that's what a battery looks like. It's not terribly important as far as how we draw our circuit, but it might be useful for us to remember that the longer end of the battery is the positive end. And then I'm going to draw straight wires at 90-degree angles. And then my resistor looks something like that. And then let's make sure we draw the complete conductive path back to the battery. And so our circuit diagram looks something like that. I might go ahead and label my resistor. I might say that this is a resistance of 40 ohms. And then I might go ahead and draw the current on there. So the current is 0.2 amps. Remember that we assume conventional current, meaning charges flow from positive to negative. And so I'm going to draw the current kind of like an arrow like that. I'm going to label it I, and that's equal to 0.2 amperes. And so the next thing we're asked to do is figure out the voltage of our battery. So in order to do that, we might use Ohm's law. Remember, Ohm's law is I equals the voltage drop over the resistance. And so if I solve that for V, delta V, multiply both sides by R to get rid of the fraction, that will look something like that. And so just substituting in the values that we've got a current of 0.2 amps, and then a resistance of 40 ohms. Instead of writing an ohm, you might write what an ohm actually is. An ohm is a volt per amp. That's what an ohm is. And so you can kind of see that the amps will cancel out, leaving us with the unit of voltage that we would expect, namely the volt. So if we do that arithmetic real quick, we would get a voltage of 8 volts. And that's all we got to do there. It's just solve Ohm's law for our missing thing and just plug in what we know. The second thing, or the third thing rather, says calculate the amount of thermal energy converted by the resistor in 3 minutes. So we're looking for an energy. So we might say something like E equals our question mark. So the thing that we have to realize is that we have a couple of different ways of figuring out the power dissipated by our resistor. We could do P equals IV, or if we plug in I equals V over R, that may look more like this. Or if instead of that we plug in V equals I times R, the equation may look like that. So again, that's just combining Ohm's law with this equation and just getting it in a couple different forms. And then the other thing that we have to realize is that power is still energy change over time. Meaning that the energy change is just power times time. And so really I could use either of those equations to solve for the power. I'm going to choose to use this last form that I wrote down. And the reason I'm choosing to use that last form is because the things that were given to me were the current and the resistance. It's also a more general form because we don't have to worry about the fact that we could have different voltages across different resistors if we had more than one resistor in our circuit. So when in doubt, that's typically the form of the equation that I use. And so if we just substitute into that, we had a current of 0.2 amps. And then don't forget we ended up with a square on that. And then a resistance of 40 ohms. And so when we do that arithmetic, we get something like 1.6, and our SI unit for power is watts. Or maybe since you're a little bit more clever, instead of writing watts, maybe it would be better to write joules per second. And that way, when we start going over here to find our energy, and we plug in the power we just got, the 1.6 value, if we write our unit as joules per second, that might help us remember that we need to take that time of 3 minutes and we need to convert that to seconds. So if you take 3 minutes and you multiply by 60 seconds, that would give you something like 180 seconds. And so the time that I need to multiply by down here would be 180 seconds. And so that would give us a total energy dissipated of 288. And then notice our seconds canceled out, that's important, so that the unit we're left with is the joule. And that's all she wrote for that question. Alright, so the second question we've got, we're told that a light bulb generates 40 watts of thermal energy when it is connected to a 120 volt source. So a light bulb is simply a resistor. It's important to realize that. And we want to do two things. We want to figure out the current through the light bulb, and then we want to calculate the resistance of the light bulb. So even though it doesn't ask me to, I'm going to go ahead and draw a circuit diagram. Circuit diagrams are kind of like the circuit equivalent of free body diagrams. We might want to draw one every single time. Since we don't know what the resistance of this thing is, I'm just going to call it R. I know that the voltage is 120 volts, so I'm going to label this 120 volts. And then the last thing I know is the power dissipated by our light bulb. I know that it's dissipating 40 watts of power. So resistance R is unknown, but the power is 40 joules per second, like that. Again, the first thing we're asked to do is figure out the current through the light bulb. So I could use Ohm's law, like I equals V over R. The problem with that is that R is an unknown. So we can either find R first somehow, or what we might do instead is use the power that's given to us to solve for the current. And so I've got P, I've got V, I can use that equation and solve for I. So if I divide both sides by V to get current by itself, it might look like that. And so we've got 40 watts of power, and we're connecting this thing to a 120 volt source. And so it might look like that. And so when you do that arithmetic, you would get something in the neighborhood of 1/3, and our unit would be amps. Or you could write that like as a decimal. Doesn't really matter. Either way you write it will be okay. And so that would be our current. Step 1 is done. Okay, second part says calculate the light bulb's resistance. So there's two ways I could approach finding its resistance. I could again use Ohm's law, as in I equals V over R, or I could again use the power. Like for example, I could use the equation P equals V squared over R, which might be preferable because we were directly given the power and we were directly given the voltage. So we do have the current over here, but as a general rule, if I can avoid using something that I had to calculate in the process of solving my problem, and I can just start over again with the initial conditions, then that's typically what I'm going to go with. So I'm going to go with this relationship to find R, and then maybe we'll come back and use the other one and see if we get the same thing. So again, substituting in what we know. Actually, let's solve it for R first. So if I multiply both sides by R, now my equation would look like that. And then to isolate R, just divide both sides by P. And then we can do our substitution. So again, we're told the voltage was 40 volts. And then don't forget about that little squared sign in there. And then we were told the power was 40 watts. No. Made a mistake. So our voltage was 120, not 40. Let's fix that real quick. And our power was 40 watts, kind of sort of like that. So if we do some quick arithmetic, do 120 squared over 40, that would give us something like 360. And again, the unit would be ohms for resistance. So just for fun, let's go back and use Ohm's law over here and see if we actually get the same thing. I'm going to take all this stuff and I'm going to kind of move it out of the way a little bit. So if we took Ohm's law and we solved it for R, then that would look like I times R equals the voltage change. And so R would equal delta V over I. And so we had a delta V of 120 volts. So 120 volts. And then we calculated our current a second ago to be 1/3 ampere. So that would look like that. What might be a more useful way to write that, just for the arithmetic's sake, instead of writing divided by 1/3, let's just kind of move the 3 up to the top, like that. And 120 times 3 would be something like 360. And so we get the same thing either way. 360 ohms, 360 ohms. So again, in general, I would prefer to use this method over here to find that resistance, just in case I made a mistake in finding my current. So that's just kind of a general rule of thumb that I always follow, just to keep myself from making multiple mistakes in the course of solving a problem. Okay, so let's look at one more example together. In this example, we've got a piece of copper wire whose resistivity we know, which is 0.2 meters long. And then we connect the wire to a 1.5 volt battery, so that would be like a D-cell battery or a AAA battery or whatever. And then we measure the current through the wire to be something like 5 amperes, which is a pretty big current. So if we draw a picture of what that looks like, So I'm going to represent the wire just as a resistor, and then act like it's connected via other wires back to the battery. We know that this is 1.5 volts. Then we've got a 5 amp current going through that resistor, and the resistor of the wire, resistance, of the wire is unknown. And that's the first thing we're being asked to find, the resistance of the wire. So again, I can use Ohm's law to do this, as in I equals, be better writing my deltas here, delta V over R. And so solving again for R, we would end up with delta V over I. And so substituting in what we're given, we know that the voltage is 1.5 amperes. And we know that the, not amperes, that would be in volts. The current is 5 amperes. And so the resistance that we end up with, if we divide 1.5 by 5, we get something like 0.3 ohms. Which doesn't sound like a very large resistance, but it's a pretty big resistance for a piece of copper. Copper is a very good conductor, and so this is a relatively high resistance for something made out of copper. So the second question asks us to calculate the cross-sectional area of the wire. So basically we want to know how wide it is. So if we kind of think about the piece of copper as being a cylinder, with a current flowing through it like this, the longer the copper wire is, the bigger its the current will be and the smaller its resistance is going to be. However, the bigger its area is, the wider it is, the lower its resistance will be and the more current will get flowing through it. So remember the thing that relates all these things. The resistance of an object, any object, can be found by multiplying its resistivity, rho, times the length over the area. And so since I know what R is, and I know what rho is, and I know what L is, I can solve this bad boy for A. So getting A by itself, I would just multiply both sides by A, get rid of my fraction. And then solving for A, just divide both sides by R. So it'd be like rho L over R would give me A. So substituting in what we know, we know the resistivity of this bad boy is 1.68 times 10 to the negative 8. So 1.68 times 10 to the negative 8. The units for resistivity are ohm times meter. And then we know the length given right here is 0.2 meters. So times 0.2 meters. And then the resistance would be 0.3 ohms. Found that just up above here. So 0.3 ohms. So doing the arithmetic, I got something like 1.12 times 10 to the negative 8. And then the unit, if I keep track of the units here, the ohms cancel out. And I've got a meter times a meter, meaning my leftover unit is a meter squared. So that would be how wide this particular resistor is. Now, if you're going, that's a really small number, you're right. But remember that a meter squared is a really big unit for area. Meter squared would be like the area of 2 desks that have been pushed together. That would be approximately a meter squared. So maybe we want to get that to be something more reasonable, like centimeters squared. So if we wanted to, we could take that number, 1.12 times 10 to the negative 8 meters squared, and we could convert it to something more reasonable, like perhaps centimeters squared. Might be a better way to think about it. So I know that there in 1 meter is 100 centimeters, but we want meters squared, so I'm just going to take both sides of that and then square it. And so when I do that arithmetic, like I multiply our answer by 100 squared, it gives me something a little bit more reasonable, like 1.12 times 10 to the negative 4th centimeters squared. And so that's still a pretty small number, but a centimeter squared would be like the size of a postage stamp, approximately. And so that's perfectly reasonable value, thousandth of a postage stamp area for the area of a copper wire. So we got a reasonable answer. It just looks kind of weird because the unit meters squared is a really, really big unit of area relative to the width of most common wires. So last thing that this question asks us to do is calculate the rate at which heat is dissipated by the wire. Now this term, rate at which heat is dissipated, is something that's very commonly used. So when you think of rate and you think of energy, the thing that we're really being asked to find is the power. Because remember that power is the rate at which energy changes, delta E over delta T. And so when you see the words rate at which something energy change occurs, then what you're looking for is basically the power. And so I'm going to use the I times V form of the power equation because I know my current is 5 amperes, and then I know my voltage is 1.5 volts. So we end up with a number like 7.5, and that would be either watts or that would be joules per second. And so that's an easy enough calculation to perform. We just have to kind of realize that when it's asking us about rate at which energy changes, it's asking about what we call power. And so we have lots of equations for power at our disposal. We just got to choose the correct one. So after doing all these examples with me, you should be armed to do all the examples that I gave you on your own. So turn your attention to those, use the ones we did together as a guide, and see if you can kind of cement this in your brain. Till next time, ta-ta.